All right. OK, so first things first, a small announcement about the midterm. It's not going to be official until it comes out in Sakai. I'm still checking with the LAs to make sure that this is going to work out OK. But I am very strongly going to think about moving the midterm a week. So instead of next Thursday, it'll be the Thursday after. No, you don't like that. Trust me, this is not good for you, right? It just means that there's that much more material that's going to be on the midterm, and now you have to spend spring break thinking about the midterm. So you might think you're happy, but you're not happy. Trust me. Anyway, so what'll happen is, and this is, I mean, I still have to, like I said, it's not for sure until it comes out on Sakai. But the idea will be that it'll be not next Thursday, but the Thursday after. The next assignment, which I promise will come out sometime tomorrow. It doesn't really matter because it involves stuff that we are going to get to today. So it will still be due just before spring break. Because if I make it after spring break, then you're not going to do anything. And then you're going to complain about the midterm and the assignment being due on the same week. Right, so the assignment due date is still going to be next Thursday. Maybe I'll push it to Friday, or maybe like the weekend, after the weekend, if people are starting spring break late. But that won't get pushed much at all. But the midterm will get pushed a week. OK, or a week after spring break. All right. So a lot of questions about midterm, I'm sure, are now no longer moot, at least for now. And I will try to come up with logistics on the actual midterm and announce those soon. OK, so we had a little snow day last week, so it's been a while. Just picking up from last time, we introduced this idea of comparable in T, right? This is an interface that basically says that two things of something can be compared to something else and put in order, right? -1 for I am smaller, 0 for we're the same, and 1 for I'm larger, right? So the only method in the comparable of T interface is compare to. And presumably, it's T that is comparable in T. In other words, like a string is comparable with other strings, or integers are comparable with other integers, or whatever. Or people are comparable with other people. However, technically, it doesn't have to be right that way. But that's what the definition of comparable in T was. And that led us to this idea of a type bound. So now that when we're building our data structures, and we always build our data structures in the most generic way possible so that we can use them with lots of different actual types, right? So now we can define a data structure like sorted array, which will work for some type T only if that type T has an understanding of what it means to be comparable to some other instance of T, right? I mean, you can't sort something unless we have this notion of ordering. And so the idea here is that with a type bound, we can put restrictions on our placeholder. So we can still program generically. We can still program to the abstraction, or we can still create generic implementations of our data structures, but we can ensure that they're only used with types that have certain capabilities. So in this particular case, we wanted to create a sorted array data structure where it's just like a list, right? Or sorted list. Actually, I should not say sorted array. I should say sorted list because that's the name of the data structure. That's unfortunate. But we wanted a sorted list data structure, which is like a list, right? It grows and it shrinks, but everything is always kept in order. And in order to do that, we need to be able to say we're going to have a sorted list of type T as long as that type T extends comparable T. So that's something new that we saw last time, this notion of placing a type bound on our placeholders, right? Then we went through the exercise of defining the data structure. So we started by saying, by providing a functional specification for the data structure. Remember what that is? It basically defines its basic operations as, or doesn't define the basic operations, but expresses the domain and range of each of the functions, basic functions on the data structure, right? So that's what a functional specification looks like. For example, the insert function for a list or even a sorted list would be something that is in the domain of lists and elements, right? Given the list, and a particular element, it will produce a instance of, it'll create a value in the range of list, right? So a functional specification is not how we're programming it, because we're going to program it in Java and be all, object-oriented, right? But it is an abstract way of thinking about the a data structure. It's the ADT, right? It helps us define the ADT, the abstract data structure, and its basic operations. The next step is then to do an axiomatic specification. And this is where the actual logic behind a data structure comes into play, right? So the functional specification just provided me with the domain and range of the various functions associated with the data structure. The axiomatic specification, remember we did this in two parts. We first identify which of these operations are canonical, which ones we absolutely must have in order to be able to create any particular version of the data structure, and then which ones are non-canonical. And then we express the constraints and logic, the semantics of the data structure by expressing axioms. And the ones we start with are simply applying all the non-canonical operations to the canonical ones. And you can, you can keep going, right? You can prove all kinds of, you can build on axioms and prove theorems and like create lemmas. Like, you could treat it very formally and model it very mathematically. We just do it at one level in order to capture the kind of the constraints that we expect to be enforced or to be true about a data structure. So, for example, we had this axiom where if we take an element and insert it into, this is a sorted list. If we take an element and insert it into a list, a sorted list, and then we take the result of that, right? So inserting an element into sorted list L, that's a canonical operation. And I am applying the non-canonical operation of removing the jth item from the result of the canonical operation. Then, depending on whether or not, if the lookup index, like where that element belongs in the original list, if it's before or after the index of where I'm trying to remove, then we have equivalent expressions, right? Where we're expressing the removal of something that we've inserted as an insertion of something we removed, right? And so we basically say removing the jth element from the result of having inserted element E into a sorted list L, right, is the same thing if the position of E, the element in the original list, was going to be less than the index that we're trying to remove, then it's the same thing as removing the j-1 element and then inserting E, right? Or if it's greater than the jth element, if the looking up the element's value in the sorted list gets an index that's greater than the jth element we're trying to remove, then it's the same thing as removing the jth element from the original list and then inserting E. The really important bit is if I insert E and then I remove index j, if the lookup value for E is j, I get back the original list, right? And so the idea here is that the actual semantics of what it means to be sorted and the implication for what it does on your operations is captured in these axioms, right? So if it's a sorted list, then this is the correct. Then this exhibits this is a statement about what is correct behavior. If I insert something into a sorted list and it belongs in the jth position, and then I remove the jth position, then I should get back the original list, right? So things like that. And we did that for a whole, all of the various sorted list axioms, from before, right? Okay. Oops. Nope. Wrong. Okay. The next thing we did was we actually implemented sorted list of type T, right? Using an array to store elements. We know that with lists we have two strategies. We can either use an array for storage, or we can use a chain of nodes, a linked chain of nodes, a linked list for storage. We happen to choose using an array, right? And if we revisit what that looked like, right? So I've kind of recreated it here. Here is my sorted list interface, right? So this is my ADT, right? So how do we actually code up an abstract data type in Java? We create an interface, right? Everything but the constructor as a declaration of what this data structure can do. So a sorted list of T that extends comparable of T can retrieve its size, look up the index that, where a particular element would belong if it was in the list, ask if whether an element is contained in the list, add a particular element to the list. Note this is different than our list ADT because we don't say where we add it because that depends on the element and how it compares to the other elements of the list, right? So we don't say add this element in the ith position. We just say add the element. There's only one spot where it should go, right? Then we can get a particular index out of the list, or we can get the smallest thing by asking for the 0th element. We can get the largest thing by asking for the size -1 element. We can remove a particular index out of the list, right? And we can remove a particular element if it exists in the list out of the list, right? So that was our interface, right? And and we could we could add other things, but this is a kind of a basic interface that captured most of what we might want to do with the sorted list. And we can imagine its implementation, right? So in implementing it, right, we have, let's see here. So here's my implementation of an array sorted list, right, which implements sorted lists, right? So now this is a specific implementation of that abstract data type. I could have a different one. I could have created an implementation based on linked lists just as easily, right? So here's an array-based implementation. And again, it only works for types T that extend comparable of T because sorted list requires a type T that extends comparable of T. So great. So I have an array of I have a type T array of elements and a size I'm keeping track of, and this basically mirrors our array-based list implementation from before, right? And so an initial size, and then here again I can't create an array of type T, but I can create an array of objects and then force it to be an array of T because all T's are objects, and so that works. And a size, right, that starts off at 0. So that's how I create a empty initial list. And then most of this is the same from before, right? So retrieving the size is just retrieve the size. One thing that we have new, one thing that we did differently was looking up elements, right? So we'll look at that in a second, right? And then right. And so let's see here. What am I trying to say? Right. So if we look at a big O analysis of the different methods on this thing, retrieving the size, constant, right? It just retrieves something, right? And we can see that in the code, right? So I'm gonna stop going into presentation mode so that I can flip back and forth with the code. So I'll just make this a little bigger. And maybe, can I make this smaller? How do I get this so that I don't see that? It doesn't matter. All right. So like, the work needed to retrieve the size is the same every time. It doesn't matter whether it's one thing or 10 things or a million things. It just retrieves that field value that's keeping track of the size. So the time complexity of getting the size of the size method is order 1. It's constant, right? Similarly, for an array list, right, an array-based list, the time complexity of get, right, if you ask, assuming index is legal, so there's some defensive programming there, but the time complexity of getting a particular index out of the list is constant because we just go straight there. That was a big difference between an array-based implementation and a linked list-based implementation. Was with an array-based implementation, we can just go straight to an index number, and with a linked list one, we would have to walk the chain, right? So that was a difference in the time complexity of different strategies for implementing this data structure, right? Removing was order n in a list. It's still order n in the sorted list because if you're removing a particular index, you have to potentially move everything passed it in the array down one spot, right? And so while the actual work of any particular removal will depend on which index you choose, right? If you remove index 0, you have to move everything. If you remove the index size -1, well, that you can actually do in constant time because you don't have to move anything. But on average, in general, right? If we, other than these special cases of the end, we would have to move on average, half the list, right? And so Big O analysis says that if you have, we only care about what the form of the function is with respect to the problem size, not any of its constants. So if you need to do something for half the items, that's order n divided by 2 is the same thing as order n. Order 3 times n is the same thing as order n. It's the function of n that we care about, right? Not the constants for how that function is shaped, right? Or translated in any particular way, right? So we can add constants, we can multiply constants. That's fine, but the point is it's linear, right? It's a linear function of that is a function of the size of the list. It's an order n operation. Lookup, right? We let's see here. Hold on. So in lookup, I'm going to put question marks here because we added this function to sorted lists where we say, okay, I want to look up the index where a particular element would belong, regardless of whether that element is or is not in the list. If it is in the list, great. Then I'll find that element in that spot. If it's not in the list, that's fine too. Lookup is going to tell me what spot it would occupy if it was inserted into the list. So that's a function that that makes sense for sorted lists. So we have this lookup function. I'm gonna delay talking about its time complexity in a second. But let's look at how long it takes us to find out if something is contained in the list. Well, if we look at the code for contain, right, we see that in order for the contain code, what contain does is it first does a lookup for that element to find the index where that element should be if it's in the list. Then it does a get of that index in order to retrieve the element that is actually there. And then it takes that and compares it to using compare to. That's the comparable part. It compares it to the element we're looking for and seeing whether it equals 0, right? And so this last line here, this expression, will return true if the ith element, where I is the lookup index for the element that we're looking for, if the ith thing in the list compares equally to the element we're looking for, then yes, this list contains that element. So now we have an operation that is made up of a sequence of other operations. So we can do a big O analysis on this by looking at its component parts. So when you have a sequence of operations, the big O analysis of the entire sequence is whichever step takes the longest, it's that. Okay? So as long as there's some step that takes a certain amount of time, or has a big O amount of time associated with it that is bigger than all the other steps, then all the other steps don't matter. It's only the step with the largest big O kind of characteristic that matters. Then the whole sequence of steps has that same big O characteristic. So in this case, then, we have a lookup followed by a get followed by a compare to. So the contains, the big O analysis of that is going to be whatever's bigger, lookup, get, or compare to. Okay? Similarly, right, if we were trying to remove an element specifically, if we look at the code for removing, where's removing? So that's removing by index, which we know is an order n operation. Removing by element, we first see if it contains the elements, and then we see if it, then if it does contain the element, then we look up where that element is, we get its index, and then we remove that specific index. Okay? So again, a sequence of operations. And so the big O analysis of that sequence is the maximum of however much time it takes us to to find out whether the element is contained or not, and then if it is contained, however much time it takes us to look up the element to get the index, and then however much time it takes us to remove by that specific index, right? Whichever one of those three steps takes the longest amount of time, or it has the biggest big O characterization, then that's the characterization for this sequence of steps. Same kind of thing if I'm adding an element, right? If I'm adding an element to my sorted list, I can implement add. We know that array lists have to be resized every now and then, and so we have to amortize the cost of the resizing, et cetera. I'm gonna brush that aside for now. Just assume that we're not going to worry about the amortization of the resizing event. But in general, assuming we don't have to resize, we first have to look up where this element goes and then move everything over, right, in order to make room, and then put that element in that spot, right? So the lookup part, right, we haven't talked about that. So that's a sequence of steps. First we do a lookup, then given the index we move everything over, and then we set that index to equal that element. Well, those three parts, right? It's the maximum of those three parts. So adding an element is going to be the maximum of looking it up, right? And then order n for for moving everything over, and then order 1 for actually setting the element, where it goes, right? The same idea here is like when we make room, it depends on IDX, but on average, it's going to be somewhere in the list. So on average, we can think of it as n divided by 2, which is the same thing as n for a big O analysis. We have to potentially move up to n things in order to make room, and so that is an order n operation, right? Okay. So the analysis of contains, remove, and add basically depends on the analysis for lookup, right? And compare to. That depends on the type, right? It could be that the specific type takes a long time to compare one thing to another thing because it has to do a lot of work. We'll just assume that the comparison part is, for our purposes, for our analysis here, is a constant time operation. And so compare to we'll assume is order 1, right? But it still means that we need to know what the time for lookup is, and then compare it to contains, which contains requires lookup, or remove by IDX, which we know is an order n operation, so we can actually replace this with ON, right? We know that's an order n operation, so that's order n, right? But the point is that some operations depend on other operations, and and if I have a sequence of operations which together is what I do for a particular method, then the big O analysis for that method is the maximum of any of the sequence of steps. So when we actually implemented lookup, right, we can do so by taking advantage of the fact that we know that our list is always sorted. And so we basically saw for the first time this notion of binary search, right? And so in this binary search, we kind of kept track of the range where this element could be, and then found a middle element, and then compared the element to the middle element, and that told us where to look next. If the element is smaller than the middle element, then it's got to be in the first half of the list, or of that range. And if it's larger, then it's got to be in the second half of that range. And so every time through this procedure, right, we are cutting the range in half as to where the element could be until we finally get it down to something trivial where we can just see, is that the element or not, right? Or is that where the element belongs or not? So algorithms that do this, anything that cuts a problem size by some fractional factor until the problem is trivially easy to do, and we can do it in constant time, that kind of divide and conquer operation will give us log n performance, right? And so the reason why it's log n is because, you know, if exponentiation is multiplying by the same factor over and over again, then dividing by a factor until you finally get to 1, right? That's the opposite of an exponent. That's the logarithm, right? And so that's why we call it log n. And it kind of makes sense, right? If you had 128 items in our list, right, then it's either going to be in the first 64 or the last 64. And then it's going to be in whichever one of those, it's going to be in the first 32 or the last 32, et cetera, et cetera, et cetera, all the way down to 1, right? And so 128 is 2 to the 7th. And so to go to 128 to 1 by dividing by 2, we have to take 7 operations, right? That's the log of 128, the base 2 log, right? OK. OK, so now that gives us the ability to complete our chart, right? If lookup is a log n operation, then contains, which is a sequence of looking up, retrieving, and comparing to. We're assuming compare to is order 1. We know get is order 1, right? And we just said that lookup is order log n. So log n is bigger than order 1. So contains is a log n operation, right? The remove is, do I contain? Well, that's log n. We just said it's log n, right? We have to, if we do contain, well, then we're going to look it up to get the index. Well, that's another log n, right? And then we're going to remove by index. And removing by index is order n. So we have a log n step followed by a log n step followed by an order n step. Well, order n is bigger than order log n, right? Grows faster than log n does. Therefore, the entire thing, that entire sequence, has O of n O of n characterization. Right? And same kind of thing for add, right? And we can see that it's the maximum of either looking it up or the order n for actually pushing everything over. And so then it's order n. OK, so if we have some number of elements and we have this sorted list, and we start off with an empty sorted list, and we add n things to this sorted list, how much time or what's the big O characterization of inserting n things into our list? Well, this is not a sequence. This is a repetition, right? So when we have a sequence of operations, the order big O analysis of the sequence is the maximum of any of the big O analysis of any of its steps. When you repeat something, then the big O analysis of the repetition is however many times you repeat it times the big O analysis of what it is you're repeating, right? Now, if you're repeating something a constant number of times, right, then you won't change, like, the big O analysis for repeating that operation a constant number of times, because I just told you constants don't matter. So we have an order n operation, and I do it 10 times, and I'm always going to do it 10 times. Then if I ask for the big O analysis for doing this order n operation 10 times, then it's 10 times the big O of n, which is the same thing as big O of 10 times n, which is the same thing as big O of n again, because we throw away those kinds of constant factors. Right? Now, but in this case, the number of times we're repeating it is related to the size of the list, right? We're going to repeat this operation n times, right? However long the list is. So if I'm going to put 100 items into a sorted list, right, then I'm going to do that 100 times. But it's but that's the idea. I'm doing it the however long the number of things I'm putting it into the list. So I can characterize the number of repetitions as in terms of how many things I'm going to put in the list eventually. So n, right? Well, I'm going to do for n times an order n operation. So now when I pull that factor in, right, and to get the big O analysis of the whole, I don't collapse back to order n. This is order n squared, which is a much is a much different thing than order n, right? So actually using our sorted list implementation to insert 100 items into the sorted list and end up with a sorted list of 100 items is going to take time related to 100 squared. right? So n squared. Now, the question then is, well, that might be just because of the way we happen to choose to implement sorted list, right? So, like we chose to use an array, and so that's the big O operation of n insertions into an array sorted list. What about if we had a linked list implementation? Would that have helped, right? So, it turns out no, right? Some things would be faster to do. So the lookup and then the insertion after the lookup, adding, actually is like we could kind of do that by walking the chain, but then once we find where we need to go, the actual insertion part, which in our array-based list required pushing things over and was an order n part. In a linked list, we know that one of the advantages of linked lists is that we can actually do the work of the insertion in constant time, because we just have to break the chain, put in a new node, and then fix the chain up again, right? And so that part got faster, but the lookup part got slower, right? So in the array-based list, we were able to, because we're able to get to any particular element directly, we were able to use binary search. But you can't do binary search for a linked list because there's no way to ask to jump to the middle of the chain. You have to walk the chain. So the lookup part for a linked list implementation is no longer log n. It's going to be order n. So while the actual work of doing the insertion got better, the work of doing the lookup ended up getting worse. And in the end, we ended up with order n for adding anyway, right? So it turns out that having done this as a linked list would not have helped any. OK. So this sorted list has order n squared performance for inserting n things because we were, essentially the reason why is because we were sorting as we went along, right? Every time, like if we were trying to insert 100 items, after we inserted 50 items, we'd already sorted, right? Those 50 items were already sorted. And then the 51st item, we still were sorted. And the 52nd item, we still were sorted. So we were sorting kind of as we went along, which meant that we ended up with an order n squared kind of performance for inserting n things. Now, we can do better if we add all the items to just a regular list, right? Which could have as quick as order 1 operation, right? Because I can add to the beginning of a linked list, that's constant time. Or I could add to the end of an array list, that's constant time. So if I didn't have a sorted list, so if I just had a regular list, I could add the n things very quickly, right? And then I could sort everything after I've already put them in the list, right? So does it help if we do that, if we wait until the end and then try to sort everything once it's in the list? Well, yes and no. It depends on how we implement that sorting functionality in that list. Right now I'm talking about just regular lists. I'm talking about adding a method to just normal lists that say sort yourself, right? So if we have a list of comparable items and we ask that list to sort itself, here's one particular example of a sorting algorithm. And if we look at it, basically what it does is it says, OK, starting with, I'm going to skip over the 0th item. I'm going to assume this list has more than one item, because that's just sorted by default. But I'll skip over the first item, the 0th item, and starting with index 1, I'm going to retrieve that element, and then have an inner for loop that starts back at 0 and goes up to, but doesn't include I. So it goes basically everything before I. And I'm going to compare the element at the in the jth spot to the element that was in the ith spot. And if I find that the ith element should belong before the jth element, right, because it's really smaller or equal to, then I'll remove the ith element and I will add it back into the jth spot, right? So this effectively will do the exact same work our sorted list does, but just all at once, right? It's basically going to, start with the 0th element as being sorted already, and then go to the first element and say, okay, from 0 up to 1, find your spot, and then you get pulled out of where you are and put where you're supposed to be. Now 0 up to 2, find for the index 2 element, from 0 up to but not including 2, find your spot, get pulled out, get inserted, and then keep going and keep going and keep going, right? So this algorithm here will work on a list, right? However, it's not going to do any better, right? It'll still be n squared. And the reason why is because we have 2 for loops, so now we can do a big O analysis on this nested for loops. The outer for loop, right, tells us how many times that work is going to be done, and it's going to be done n times, right, because it's going to go up to the size of the list, right? I mean, we get 1 for free, but in the limit, we're going to do this outer for loop n times. When you have a repetition, right, the big O analysis of the repetition is however many times you do the repetition times the big O analysis of what you're repeating. So this outer loop is going to happen n times. And so we're going to say, OK, the big O analysis of everything is n times the big O analysis of what's inside the outer loop. What's inside the outer loop is, well, a get. OK, so array-based implementation, that could be constant time. But then here, where we're going from 0 up to I, and I is going from 1 to n, we basically have another order n operation here, right? And so I have n repetitions of something that is going to be, because I is going to eventually get up to n, right? It's going to go from 0 all the way to n. And so, for an order n body, right? N times order n squared. So this doesn't do any better, right? However, we can do better, right? And without getting too far into it, because you'll learn this a lot in more detail in 550, there's an algorithm that's called quicksort. And quicksort is a recursive sorting algorithm that does better than n squared, right? And the way it works is you basically quicksort a range within a list. So you have a start to the range and an end to the range. And what the basic idea is you pick an element in that range to act as what's known as the pivot. And you rearrange the elements in that range so that you have everything that is smaller than the pivot at the beginning of the range, then the pivot item, and then everything that's larger than the pivot at the end, past that part, the pivot item. And so you basically now have rearranged your range to have 2 areas. Everything before the pivot, everything that's smaller than the pivot, and everything that's larger than the pivot. And then you recurse on those subranges until finally you get to the base case where you just have a range that only has 1 item in it. That's essentially already sorted, and then you're done, right? And so, right. So why does this end up doing better than n squared? Well, because it turns out it depends on its implementation, right? We need to be a little bit clever about its implementation. But if we use an array-based list, then we can actually do this. So I have a little. This little video actually demonstrates how this quicksort step occurs and how we can do it, very efficiently using an array. The video is worth watching, so we're going to watch it. It's got some excellent music. So so basically, we'll watch the video and then we'll rewind it and I'll step it through it a little bit. Hold on, let's get back to the beginning. Make sure our volume is on. Oh no, where's the sound? The sound's the best part. Oh, hang on. How did the sound not come in here? All right. I haven't sent it to the projector. That's why. OK. Here we go. So we're selecting a pivot, and we're keeping track of I and j. And essentially, we're looking for something that's smaller than the pivot. We advance I, we swap I and j, and we keep going. Right? As long as it's smaller than the pivot, we advance I, switch I and j, keep going. Right? Bigger than the pivot, bigger than the pivot, smaller than the pivot. Advance I, swap I and j. Right? Smaller than the pivot, advance I, swap I and j. Now we're done. J is done with the list. Now swap I and the pivot. Stop. Now, look. Boom. Right? What did we end up with? We ended up with the pivot in the middle, right where it's supposed to be, and everything lower than the pivot before it, everything larger than the pivot above it. Okay? So that is one step of quicksort. And now we can recursively apply quicksort to everything below the pivot and recursively apply quicksort to everything above the pivot. Okay? So, right, and so then the video keeps going. That was kind of tricky, right? That one, it actually, everything was already smaller than the pivot. We just needed to, at the end, swap the pivot and I. So, right? We have P. I starts where P starts. So P starts at the beginning, right? I starts at the beginning also. And then we have J, which starts one afterwards. And we start looking. Is this smaller than the pivot? Yeah? Well, then advance I and swap I and j, and then keep going. And so we advance I. And now swapping I and j, it's the same index, so it doesn't really go anywhere. Right? And now we keep going. Advance j. Is that smaller than the pivot? Yeah. Advance I. And now swap I and j. Smaller than the pivot, advancing I, right? And now, so that's the advancing j all the way through, right? And and now the last step is to swap pivot and I. And now it's going to do the other side. Okay? All right. So I think that's plenty of fun. You can watch the whole thing later. But hopefully you can see how this is going to end up. Right? At the end of the day, we'll end up with all of with everything in sorted order. The very end of the video has a nice little graphic that we'll come back to. I just want to switch back to the slides real quick and talk about a couple of things. Okay, one thing that whole algorithm and its kind of explanation kind of brings up, and this is we're going to see this more and more when we start talking about data structures and what their invariants are. Right? What's an invariant? An invariant can apply to a data structure. And it can also apply to an algorithm or to a certain spot in an algorithm. But invariants and being able to identify and an invariant can very much help you debug your programs, because it basically says if everything's going to plan, then I can tell you exactly what must be true. In some sense, invariants are a little bit related to our axiomatic specification, right? The axiomatic specification basically says if you apply this operation to the result of this other operation, here are expressions for what must be true, right? So if I remove the ith element from a list where I just inserted the ith element, then I should get back the original list, right? That's an invariant, right? Right. So an invariant is something that's always true at a particular point in an algorithm, right? So at the beginning step of quicksort, right? What is invariant, or at each step of quicksort, what is invariant with regard to the elements of the array, right? Well, if we look at any point in the quicksort algorithm, right, which basically keeps track of three indices: a pivot indice, which we always make the start of our range, the I index, and the J index, right? And that's how it works, right? If we think about the elements that are in our range as quicksort is operating, and think about the invariance for what must be true for those elements relative to those indices, we can kind of begin to understand why and how the algorithm works, right? In particular, right, everything that is all the elements from the pivot element to I, they're always less than or equal to the pivot element. And everything from I to j is always greater than the pivot element. And that's always true, even as we go through and swap I and j. Like that's at the beginning of every time we advance j and see if it's smaller or bigger than the pivot element, and then advance I and possibly switch or not, right? We are constantly making sure that this invariant is true, until we get to the very end of a quicksort step, where we now have everything from p, which is the very beginning of the range, to I, that's either smaller than or equal to the pivot element, and everything from past I to the end of the list is bigger than. And then the last bit of quicksort is to swap the p element and the I element. We know that the p element is at least as big as everything in that range from p to I, and we know that everything past I is bigger than the element at the pivot point. And so when we do that swap, we know that everything before that pivot still has to be less than or equal to everything before I still has to be less than or equal to our original pivot element, now that we swapped them, right? And everything after still has to be greater, right? And which also means that once we've swapped I and p, that pivot element is now in the right spot. It ends up, no matter what the other elements do and how they end up sorting out, this element is now in the right spot, right? Okay. So what kind of list implementation is best for quicksort? Well, if we look at the operations it needs to do, it needs to be able to get to subranges of its lists very quickly. It needs to be able to swap things around in its list very quickly, right? If those operations take time, then quicksort is going to take time. So we want the component operations of quicksort to take a small amount of time as possible. And in this particular case, while we could try to implement quicksort in a linked list, it really wouldn't work very well, because we don't have random access. We can't swap items in a linked list. So quicksort only really works on a list-based array, right? There might be some other kind of sorts that also has good performance for linked lists, but it's not quicksort. So the operations of quicksort lend itself specifically to an array-based implementation, right? So then how long does quicksort take? What is its big O analysis? Well, one thing to note is that we always, at every level of quicksort, we're always looking at all n elements, right? The first level of quicksort, where we start off with the first element as the pivot, the thing that we just saw the animation for, that j went from the beginning all the way to the end, and we found where the pivot goes, and now we have two subranges of everything smaller and everything greater. So that first step was an order n operation, right? All the individual swaps, all that stuff, that's all constant time. So it was just however long it took us to get through j, right? Get through all of the things. At the end of that first step, we end up with one element in the right position and two smaller problems, right? So then the two smaller problems, it doesn't really matter whether half ended up in one range and half in the other range, or 1/3 ended up in one range and 2/3 ended up in the other range. It really doesn't matter, how they got divided, because when we solve the smaller problem for the smaller range, and then we do quicksort for the larger range, the total amount of things that we're going to have to scan is going to equal n again, right? So every level of quicksort basically involves looking at n things and putting them, either swapping them or kind of moving them around or putting them in the right spot, either before the pivot, after the pivot, or it is the pivot. So each level of quicksort, right, as the problems, as it divides into different ranges, each level across the different problems on that level is an order n operation, right? Now, so that's for each level. Now, how many levels do we have? And that's where quicksort becomes really fast, right? How many levels we have? Well, that does depend on how things get divided. If, in the best case, we divide the list into exactly 2 equal parts, then every part, right, is getting half as big. And so the number of levels we need to get to before we're down to the trivial, there's only one item in the list level, is going to be log n. And so every level, across every level, the subproblems sum up to an order n operation. And there are log n levels. That means that quicksort as a whole is n log n. And that is as fast as you can sort anything. So there is a fundamental limit to how fast you can sort shit, and it is n log n. So if somebody is telling you they have a faster sort than that, they're lying, right? It's like a perpetual motion machine, right? We can kind of see this structure in the animation later on. They kind of show it. Right? So we start off with quicksorting the whole thing, and then we're quicksorting 0 through 3, and then we're quicksorting 0 through 2, until we finally are quicksorting something that is totally, trivial, right? And then the other side, right? So the idea is that at the top level, that top level took order n. At the second level, it's split one way or the other, but across both of those splits, there's going to be an order n amount of work to do. And then the next level, again, it's split however it's going to split and getting smaller, but across all of the quicksort steps on that level, it's going to add up to order n operations. So each level, across all of the things you're doing at each level, it sums up to an order n operation, and then we just need to know how tall this tree is, right? And so how long does it go down? And that is log n, if we split things by 2 each time. But there is a worst case that is much, much worse, right? If the list is already in order, then what will happen is that we'll split it up into something trivial and then everything else, and then something trivial and then everything else, and then something trivial and then everything else. So what will happen is that the number of levels we're going to need for the tree is not going to divide by 2. We're going to end up with n levels. So in the worst case, quicksort goes back to being order n squared. If it's all already sorted, right, then it ends up basically sorting everything to find that the pivot is exactly where it needs to be, and then cutting it up into 2 problems: an empty problem, everything before the pivot, and then the n-1 problem, everything after the pivot. But then it's going to find that it's already sorted, and so there's an empty problem and an n-2 pivot, and we're going to have, so basically the tree is, one side of the tree is always going to terminate, the other side of the tree is going to keep going down, 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 until we have n tree levels. Order n across each level, n tree levels, order n squared. So quicksort only works if, in expectation, there are certain worst case inputs that can make it order n squared. Okay. Which brings us to the idea of trees. So trees are our next data structure. Okay? So a little bit of a change of pace here. In lists, elements in the list had a relationship and had an ordering relationships with each other, right? In a sorted list, they were ordered by their comparableness. In just a regular list, they were ordered by where they were put in the list. So the 0th item comes before the first item comes before the second item, right? There's a notion of where you are in the list, right? So that's lists. Hierarchical relationships are often modeled by trees. And in a hierarchical relationship, we think of every element as being a node in the tree, and that those nodes have children, right? So instead of just a simple ordering of elements, now we're talking about a relationship between elements where we have a notion of being higher up in the tree and lower level in the tree, right? So just a little bit of nomenclature. Every element in a tree is stored at a node. A node might have one or more children. And those children are ordered. So just like your siblings, right? Your parents had a certain number of children. There's a first child, and then a second child, and then a third child, right? And so the children have an ordering amongst themselves, but a node in a tree has potentially one or more children, and those are ordered, right? Every node has exactly one parent, right? So whoever I am a child node for is the node that is my parent. We can define the root of the tree as the node that has no parent, right? The node at the very top of the tree that has no parent is that special node is a root. We can also think of nodes at the bottom of the tree, the nodes without any children, right? So actually, internal nodes have one or more children, but leaf nodes, the ones at the bottom of the tree, have 0 children. They don't have any children. And so those nodes are known as leaves, right? So, right. The depth of a particular node is simply how many levels down from the root you are. And then the height of a node is the distance between a node and the furthermost leaf that's underneath it in this hierarchy. And the height of the tree as a whole is the same thing as the height of the root node, right? It's the distance between the root node and the farthest away leaf, the farthest away node that has no children. All right. With that, let's do a little Sakai thing. Given those definitions, right, we have let me open it up. Woohoo! I still have to publish it, sorry. With those ideas in mind, let's take our little participation quiz. Why not? Unless I can't find it. All right, it should have just been published. All right, so it basically asks these questions. Which element is the root element? Which elements are leaves? What is the height of the tree as a whole? And what is the depth of the RE element? I'm going to give you just a second to think about it and do it, right? So feel free to confer with your neighbors. Again, like with all of these in-class quizzes, in the end, they're going to go in the grade book as whether you were here and you did it and you submitted something or you didn't. So there are right answers and there are points, but that's not going to affect your grade. That's just how I set up the quiz so that you know whether you got it right or wrong. But in the end, I will fix things so that it's either you participated or you didn't. So I'll give you one more minute. All right. OK. So while you're finishing that up, we can go through the answers. What's the root element? That should be pretty obvious. It's the thing at the very top, right? Lo, L-O. That's the root element, right? Which elements are leaves, right? Well, the ones that are at the bottom that don't have any children of their own. So ti, fa, mi, and so are all leaves. Right? What is the height of the tree? The height of the tree is the same thing as the height of the root element. And that means it's the longest path from the root element to the furthest away leaf. So even though so is a leaf and it's only 2 levels away, the height of this tree is not 2, it's 3, because there's at least one leaf, actually 3 leaves, that are 3 levels away. Right? So the height of this tree is 3. And then what is the depth of RE? The depth of a particular element is the distance between the root and that element. So the distance is 2. Right? So we start at low, that's a depth of 0, and then go to its child OK, that's a depth of 1, and we go to RE, that's a depth of 2. Right? And so the height of the root is going to be the same thing as the depth of the furthest away leaf. Right? So ti, fa, and mi are all at depth 3, and the height of the tree is 3, because that's the depth of its furthest leaf. OK, so with that nomenclature in mind, let's think a little bit. There's a really cool thing about trees. And if you really, really want to learn data structures, I highly recommend taking a day and going to a park and tripping shrooms, because that shit will fuck you up. But you will stare at a tree, and you will really begin to understand data structures. Right? It will speak to you. So if we think about a tree, what's really cool about a tree is if you plucked one of these branches off and just pretended, rotated in your mind, and put it in the ground, and on shrooms doing this exercise, it really does work, right? Then what do you have? You have another tree, right? And you can take one of those branches, and you can pull it off, put it in the ground, and it looks like another tree. And it just goes on and on and on and on, and then 3 hours go by, and the trip's over, and you're sad. So OK, so trees are recursive data structures. Turns out, so are lists. I just didn't tell you that, right? And we'll go back to lists and look at it as a recursive data structure later. But trees are recursive. It means the children are just trees, right? And so, when we look at a tree like this, right? The tree is a root with 0 more trees underneath it, right? So we can think of that as being a tree, right? And that as being a tree. So if we pull off that branch and then just look at it, it's a tree. And if we pull off that branch and look at it, it's a tree, right? And so on and so forth. And so until we get to the very bottom, right? Now, at the very bottom, for the leaves, in order for everything to be a tree, we do have to create a special case for an empty tree, a tree that doesn't even have a root element. It's just literally a tree of height 0, right? Or not even height 0, almost like height -1. It doesn't have anything. It's literally empty, right? It doesn't even have a single element in it. A single element tree still has a root. It's that element that's at that root. And then it has empty trees as children, right? Or no children. An empty tree is basically nothing, right? It doesn't have an element, doesn't have children, it has no height, it has no depth. It's just literally empty. Okay? All right. One last thing about trees is this notion of arity. Okay? So a tree has an arity. That's the maximum number of children any of the nodes in the tree has. Okay? So in this case here, this is a arity 3 tree, because there's at least one node that has 3 children. OK. So what are trees good for, right? What are these n-ary trees good for? Turns out they're good for a lot, and they come up in a lot of different things, right? You can think of a file system as being a tree of directories, right? In a file system hierarchy. You can think of parsing something. Will generate syntax. Parsing a language or parsing a language will result in what's known as a parse tree. Right? We can think of family trees. We can think of family trees of mythical beings. We can think of like organizing car models as trees, or org charts, or different kinds of scientific models, or biological classification, right? All of these things are essentially trees. So hierarchical relationships among data come up so many different ways, right? And so trees are going to be one of our most important data types. All right. In particular, we're going to care about binary trees, right? So yes, we might want to generalize to n-ary trees or trees of a particular arity, and that's fine. But binary trees is where we're going to start, because this specific special case comes up a lot, is easy to work with and to analyze, and we don't have to worry about so many kind of like generalizations, like because it kind of collapses to, there are certain things that we don't have to worry about for binary trees that we would have to kind of, I don't know, get a little bit messy if we want to generalize to trees of any arity, right? So we're going to start by studying binary trees. It's a special case of an n-ary tree where the arity is specifically 2. When we have a binary tree, we don't talk about the first child and the second child. We talk about the left child and we talk about the right child. And for the only thing in the world in which left comes before right, I'm left-handed, so I'm a little pissed off about everything. The left child is considered the first child. Okay? So when we look at a binary tree, if we draw it, we'll draw the node, and then we go to the left, that's its left child, and to the right, that's the right child, right? So binary trees have a left and a right, right? And it's ADT, right? We'll start by defining its abstract data type, right? So here's an interesting bit here. Because we're going to be recursive, okay? We have to have a way of creating a tree, right? We have to have a way of the base case. The very bottom case has to be something we can create directly. So we're actually going to have 2 constructors here, right? There's a special case for the empty tree. So when we ask for a new empty tree, we don't have to provide a value, right, for the element that's being stored at the root node of that tree, because there is no root node of that tree. It's literally an empty tree. But it's still a tree. And everything is well defined on an empty tree, right? How do we know it's well defined? Because we're going to do an axiomatic specification. And so we're going to define what it means to set the left or get the left of an empty tree. Some of it will be an exception, right? Some of it will be an error. But the point is that we have 2 canonical operations for creating trees. We have the canonical operation that can generate an empty tree. And then we have the canonical operation that says, you give me a value, that's what's being stored at the root, and then the 2 subtrees, the left and the right, and I'll give you back a tree, the tree that has that value, and then this left, the left you provided and the right you provided. Obviously, given a tree, we can ask for its value. It's the value of whatever's at the root node, right? And whatever we stored there, right? And of course, getting the value of an empty tree is still well defined. It's nonsensical, but it's well defined. It's an exception. It's an error, right? We can get the left and get the right. For the regular tree, right, it's obvious, right? If we have a value and then a left child and a right child that we munch together to be a tree, then when I get the left from something that is the result of that new operator, I get back one of those trees, like whichever one you want to call left and whichever one you want to call right. So presumably the first one. Getting the left and right on an empty tree, that's an error, right? You can still do it, right? I mean, it's something we have to define it. We have to think about that case, but we're going to define that case as being essentially an exception, an error, right? We can set the left and set the right, right? Given a tree and another tree, then we want to say, okay, give me the tree that results if we set the left child of this tree to be this other tree. That actually does work on empty, right? If I set the left of an empty tree, I basically get the result of creating a new tree with empty on one side and whatever. No, actually setting left doesn't work. No, okay, yeah, that's also an exception, right, for an empty tree. And then, of course, the height, we can ask a tree for its height, right? So that might be my abstract data type, my functional specification for my binary tree, right? Okay. So given that abstract, that functional specification of an abstract data type, we can turn it into an interface, right? So here's my interface for a binary tree, right? It's basically that functional specification turned into methods on an object, right? Obviously the constructor, that goes in the class, so we don't have that as part of the interface. But we can retrieve the value of, so this is a binary tree of type T. The type T here is the type of whatever's stored at each node. So if it's strings, then it's a binary tree of strings. If it's numbers, it's a binary tree of numbers. But the point is that I can ask for the value of a tree. That's the value stored at its root node. And then I can retrieve recursively, right? And so this is the recursive part, right? But when I ask for the left part of a tree, I get back another tree, right? And I can get the right, I can set the left and set the right, and I can ask for its height, right? All right. So we have 5 minutes left. I'm gonna we can implement empty tree. That's actually pretty trivial, right? We can say, okay, give me a new class, and it's going to be empty binary tree of type T, and it's going to implement the interface binary tree. There it is. All right. Voila. Right. Okay. It's going to have nothing. It's going to have absolutely nothing at all, right? There's no value here. There's no trees here. There's left, no right. So it doesn't even have to have fields, right? If it doesn't have fields, it doesn't even have to have a constructor. So what's its value of getting an empty tree? That's an exception. There is no value. Right? What's its left? No left. No right. You can't set anything. You can't do that. Right? And oh yeah, this doesn't even make sense either. Right? So this is my definition for a binary tree. It works, right? It's an empty binary tree who's defined axiomatically to throw exception for all of its operations. But it's still an empty tree, right? It's still a tree, right? And the reason why this is good is because when we are trying to create trees which have a left and a right, but we're a leaf, that's what we're going to point to. Our left will be an empty tree, and our right will be an empty tree. So in our recursive definition, our leaf nodes, right? We don't need nodes anymore. We just have tree. Trees that happen to be leaves, right? Which means that they don't have any children, will still have a left. It'll just be an empty tree. And they'll still have a right. It'll just be an empty tree. And so by defining empty tree, even though it's trivially dumb, right? It gives us a type that we can use that is a tree that we can set to our left and our right. When we have this kind of situation, often what we'll do is we'll just use the value null to mean empty tree. And that is typically how binary trees really are implemented, is that they don't bother creating an empty tree type to represent essentially no tree at all. They just use the special value null to be the same thing. So on Thursday, we'll pick up there, and then we'll talk about binary search trees, which is a special type of binary tree that lets us look up and insert things in order, which is how it gets connected back to our quicksort lecture. And the assignment, which will come out later tomorrow, is going to be an implementation of binary search trees. So pay attention on Thursday.